Hey everyone, welcome back to Calculus 3. This will be lecture 5 of the course. And in this section, we're going to continue with our mathematical description of 3D space. And we're going to talk about lines and planes in space. So we're very used to talking about lines in 2D space, very used to that by now. This is going to take lines and move them into three-dimensional space, and then we're going to also discuss another thing that can happen in 3D space very commonly, and that is the existence of planes, multiple planes, and how they intersect and how they work with each other, etc. So let's go ahead and jump into it. Okay, so again, this is going to be section 1.5, lines and planes in space. Okay, so we're going to start by kind of describing how we can begin to think about slope in space. Okay, so in the plane, it's a logical place to start with is with this idea of slope. So in the plane, slope of a line is used to determine the equation. Okay, so in the plane, slope is used to determine the equation of a line. Now in space, because it's not a surface any longer, in space it's better to use vectors to determine the equation of a line. So in space, we use vectors instead. Okay, and we'll see exactly how in a moment, but the idea of slope kind of breaks down a little bit in 3D space. It's still a concept, but it's not something that we want to use a whole lot. Instead, we want to use vectors. Okay, so let's draw some pictures and start talking this through. Okay, I'm going to try to draw a 3D coordinate system here. Okay, we'll say this is your x-axis, your y-axis, and your z-axis. And now let's consider a line in this space. Consider a line L in space, and we're going to have it go through a point P. Okay, so I'm just going to draw a random line here, and then we're going to have this point P. Okay. Now, this line L, is going to be parallel to a vector v. Okay, and so I'm going to draw v in here, and I'm going to try to make it look parallel. Okay, but you'll just have to accept that that's meant to be parallel to the line L. Right, so this is the line L. L goes through P and is parallel to V. Okay, and let's go ahead and put some notation on V. So V is ABC, we'll say. Okay. Now, V is parallel to the line L, okay, and V is equal to ABC, right? The components are A, B, and C. Now, V has a name with regard to L and is called the direction vector for L. So V is the direction vector for L. Okay, and ABC, the components of V, are called the direction numbers. I mean, this is one way of speaking about it, right? They're called the direction numbers. So much of math is just giving names to things and stating how things relate to one another. So we need these names: direction vector, direction numbers. Okay, now let's talk more about this line L. So one way of describing this line, one way of describing this line one way of describing L would be by saying, it consists of all points Q, right? And Q is going to be XYZ points, right? Points in space. It consists of all points Q for which the vector PQ is parallel to V. Okay, so does that make sense? So if I put another point on here and call it Q, okay, now Q can be any point on the line L, right? But the way one way to think about L is by saying that it consists of all such points Q, where if you take P and Q and create a vector, that vector would be parallel to V, right? So Q could be back here, it could be over here, it could be up here, wherever it happens to be. If it's on L, it's going to form a vector that is parallel to V. Okay, right? So that being the case, what we can say the following. So then if, let's label P here, let's call it X1, Y1, Z1. So if that's P, we can say that the vector PQ is a scalar multiple, right? It's a scalar multiple of V, right? So it's a scalar multiple of V. They have the same direction. They may not have the same magnitude, but they have the same direction. Okay? And that being the case, we could write the following. We could say PQ is equal to, remember, it's just going to be X minus X1, Y minus Y1, Z minus Z1, right? And that's going to be equal to whatever A happens to be times some scalar T, and then BT and CT, right? Which is basically just V multiplied by some scalar T. All right. Okay. So this leads us to a very nice way of representing lines in space. Okay. What we can do is then we can equate. So by equating corresponding components, we'll get the following parametric equations. Okay, and so what I mean by corresponding components are like these two here. So x minus x1 is equal to at, and then y minus y1 is equal to bt, z minus z1 is ct. Right, so let's go ahead and lay this out quickly. Okay, and so here's a theorem. It's basically going to recap everything we just talked through. So a line L parallel to the vector V equals ABC, and passing through the point P, X, Y, Z is represented by, okay, and you can, here's the system, here's the parametric equations. You got X equals X1 plus AT, Y equals Y1 plus BT, and Z equals Z1 plus CT. Okay. All right. Okay. Perfect. Let's call these X1, sorry, X1, Y1, Z1. Okay. All right, so that being the case, now we could take this further. And so if, what we could say is that, if the direction numbers A, B, and C if those direction numbers are all non-zero, we could eliminate the parameter t. And we could get a different set of equations. Basically, what we could do is we could say, for example, x equals x1 plus at. Well, that implies that x minus x1 equals at, which implies that x minus x1 over a equals t. And we could do that for all three of them, and since they all equal t, we could equate them, right? And we'd get a symmetric equations. So this would produce basically x minus x1 over a equals y minus y1 over b, which would be equal to z minus z1 over c. Okay. All right, very good. Let's do an example. Let's do an example of this and see how this can work in practice. Okay, so we want to find a set of parametric equations of the line that passes through, we'll just use -2, 1, 0, and 1, 3, 5. Okay, so I got 2 points in space. It's going to be a line going through those. And we want to figure out, we want to write down the set of parametric equations to describe that, that line in space. Okay, so first thing we're going to need is a direction vector. How might we get a direction vector? Direction vector. I don't know what I was writing there. That's just supposed to say vector. There we go. Like I was writing direction vection or something like that. All right, so a direction vector. How could we find a direction vector? Well, we're given 2 points. Easy enough to identify a vector from those 2 points. All right, so we'll say v is equal to pq in this case. And to find the vector pq, we subtract. All right, we're just going to take basically q and subtract off p. So we'll have 1 minus -2, and then 3 minus 1, and then 5 minus 0. Again, just kind of going 1 minus -2, 3 minus 1, 5 minus 0. Okay, and so that gets us to this vector 3, 2, 5. Okay, now that's going to be our ABC. All right, so this is the direction vector, this is the direction numbers. All right, so in this case, the line PQ is used to define the vector itself. Okay, that's not always going to be the case, but in this case, that's how we're going to do it. Okay, so then what we want to do is we want to write out the parametric equation. So using the direction numbers, okay, and so for that it'd be A equals 3, B equals 2, C equals 5. And we can use that, we have to use that together with one of the 2 points. Let's just take the first one. So using the direction numbers and the point -2, 1, 0, we can write out these equations. So we've got x equals x1 plus at. Well, x1 is just going to be your -2, and your a is 3. So -2 plus 3t. Y would be y1 plus bt, okay, which is 1 plus 2t. And z is z1 plus ct, which z1 is 0, and c is 5. So this would just be 5t. Okay, so those are the parametric equations which describe this line in 3D space. Now, how does this work? Now, how do parametric equations like this work? So as t, a real number, varies, right? As t is a real number and it varies, the set of equations will basically determine all of the points on the line. Okay, on the line PQ. Right, so you plug in different values of t. So if t is equal to 3.6, you plug that in, you get a point on the line. If t is equal to 3.7, you plug that in, you get a point on the line. If t is equal to 1,000,000, you plug that in, you get a point on the line. So all of the points on the line can be derived by some sort of systematic entry of these values of t. Okay? Hence the name, the equations which describe the line. All right. Okay, so that's kind of how we want to, that's a good starting place for how we want to think about lines in space. There are other things we can do, of course, and we'll see some of those later. But this is where we want to start. Okay, I want to start with this. All right. Let's move on and discuss planes in space next. Okay, so next we want to talk about planes in space. Not airplanes in outer space, but surfaces in 3D space. Okay, so for lines in space, right, so what we just talked about, those equations can be determined basically from knowing a point on the line and then just a vector parallel to the line. Okay, so if you have a point on the line, you need at least one point on the line, and you need a vector parallel to it in order to determine the line in space. It's a little bit different for planes. Okay, let's summarize. So just for lines. So for lines, we need a point on the line and a vector parallel to the line. That's what we just saw, right? We were able to derive those parametric equations by knowing a point on the line and a vector parallel to it. Now for planes, it's different. The requirements are different. So to see how a plane in space can be determined, what we need is a point in the plane and a vector that's not parallel to the plane, but normal to it. Okay? Normal means perpendicular. Okay? So for planes, we need a point on the plane, or in the plane, maybe we say. We need a point in the plane and a vector that is normal to the plane. Okay, a vector that is 90 degrees to the plane or perpendicular to the plane. Now, that may seem kind of like an interesting combination of things to need in order to describe a plane. The normal vector in particular, when you first come across that, you may think, why? How's that going to work? It's actually rather ingenious. So let's draw a picture here and see how this all works out, right? So let me try to draw a plane first. Now, it's assumed, right, that these planes are infinite, but I just, obviously I'm on a sheet of paper here, so I'm just going to draw like a little flattened edge. Okay, and so I'm going to draw a point P in the plane. Okay, and then when we draw this coming out like this will be our normal vector. And what does that mean? Well, normal, of course, means that it's at a right angle to the plane. Okay, and so we want to consider a plane like this that contains the point P. So this plane contains the point P, and P will be XYZ. Okay, so P is XYZ. It has a non-zero normal vector n, which we'll call ABC. Okay, so some normal vector n. And now, one way to think about the plane is to think of the plane as consisting of all points Q. All points Q. Okay, so this plane consists of all points Q. Okay, and we'll call those X, Y, Z, such that the vector PQ is orthogonal to n. Okay, does that make sense? That's kind of ingenious, right? So you've got this normal vector and you've got this point P, right? So the normal vector extends outward from the point P at a 90-degree angle to the plane. Okay, now the plane can be thought of as the collection of all points Q such that the vector PQ is orthogonal to n. Okay, that's very convenient because a lot of the vector ideas that we've already been discussing deal with orthogonality. So what happens here? If that's the case, then we know that n dotted with PQ is 0. Okay, so let's write that out here. What does that mean? Well, that means ABC, that's the normal vector, ABC, dotted against PQ, which would be X minus X1, Y minus Y1, Z minus Z1. Okay, that's going to have to be equal to 0. Right, so dot products is a scalar, right? So this is all fine and dandy to do. I'm just expanding this dot product over here. So we can derive the equation for a plane using this. And what we see is that A times X minus X1 plus B times Y minus Y1 plus C times Z minus Z1 is equal to 0. Okay, this is the equation of the plane. Okay. All right, and this is the standard form. Okay. All right. So this is the standard form of the equation of a plane. Okay. In 3D space. So we'll just rewrite that. Just a little bit cleaner and more concise. Some people really like that. They like their theorems to be clean and concise. So the plane containing the point x1, y1, z1. Okay, and having a normal vector n equals ABC can be represented in standard form by basically this equation here. So A times x minus x1 plus B times y minus y1 plus C times z minus z1 equals 0. Okay? Very good. All right. Very good. Let's do an example and see how this all plays out. Okay. Let's do an example. All right, let's say we want to find the general equation. Find the general equation of the plane containing the points and we'll have 3 points here: 2, 1, 1, 0, 4, 1, and -2, 1, 4. Okay, so it's going to take 3 points to define a plane, right? 3 points to define a plane. If you just give me 2 points, then there's an infinite number of planes that could envelop those 2 points. So you need 3 to define a unique plane. Okay, so from these 3 points, we can construct 2 vectors. Okay, right? So these three points can be used to construct 2 vectors. Let's do that. Let's call them u and v. So the u vector we'll get from basically subtracting this point from this point. Okay, so we'll say u is equal to 0 minus 2, 4 minus 1, and 1 minus 1. Okay, and so what do we get? We get -2, 3, 0. What about v? Well, for v, we're just going to subtract this point from the first point. Or sorry, we'll subtract the first point from this last point. Okay, so we'll get -2 minus 2, and then 1 minus 1, and 4 minus 1. And so we'll have the vector -4, 0, 3. Okay, so 2 vectors. Okay, now both of these vectors are obviously in the plane, right? They have initial and terminal sides, right? Think of them as directed line segments. They have initial and terminal sides, or points in the plane, and so naturally they lie in the plane. Okay, so so once you have these 2 vectors in the plane, what we need is a normal vector. How do we find a normal vector, a vector that's normal to the plane? Well, I've got 2 vectors in the plane, so we can use the cross product on those 2 vectors to find an orthogonal vector, right? i.e. a normal vector. So that's what we do. So we say n then is equal to u cross v. You could just as well do v cross u. And we can crank out that cross product really quickly, right? Just lay it in here. We know that it is the determinant of this. And so, again, crossing out the I, you would get 3 times 3 minus 0 times 0. That's your I. So you get 9i, and then it'd be minus, and then you would get -6 minus 0, so -6j, and then plus 12k. Okay, and so that vector is 9, 6, 12. That vector is normal to the plane that we're describing here. Okay, so hopefully those steps are straightforward, right? We start with 3 points in the plane. From those, we can derive 2 vectors in the plane. From those 2 vectors, we can use the cross product to identify a normal vector to the plane. Okay, and once we have that normal vector, we know the direction numbers. Okay, so we can say a equals 9, b equals 6, and c equals 12 are the direction numbers for the plane. Okay. Okay, and so then what can we do? Well, we just plug all of this into the standard equation form. Okay, so we've got using these, and you can pick any of the 3 points up above, but let's use x1, y1, z1 equal to 2, 1, 1. Okay, let's just use that. We'll plug that into our standard equation. So our standard equation looks like this: a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. And so just plug all of this in, and we get 9 times x minus 2 plus 6 times y minus 1 plus 12 times z minus 1 equals 0. Okay, and then we can distribute and kind of clean this up a little bit, so we get 9x minus 18 plus 6y minus 6 plus 12z minus 12 equals 0. And so we have 9x plus 6y plus 12z minus 36 equals 0. So adding 18, 6, and 12, negative, we get negative 36. And then we could divide this down. We could simplify this by dividing everything by 3. And so we get 3x plus 2y plus 4z minus 12 equals 0. Okay, and that is the desired equation for the plane that we're asked to find. Okay, and so this would be the equation in standard form. Okay, so this would be the equation in standard form. Now we can confirm that we were given these 3 points at the onset, right? We could confirm that these points indeed satisfy this equation, right? So let's plug in the 0, 4, 1, for example. Let's plug this one. We use this one to derive it, so let's plug this one in just to confirm that this is indeed an equation for the plane. Well, all we'd have to do is say plug in 0, 4, 1, so it'd be 3 times 0 plus 2 times 4 plus 4 times 1 minus 12 equals 0. That's 0 plus 8 plus 4 minus 12 equals 0. And of course, you're going to get 12 minus 12 equals 0. So true, right? Okay, so obviously this is an equation of, well, at least the other point in the plane is in this one as well. Okay, excellent, excellent. So we've talked about lines in space and how we can use parametric equation, a particular set of parametric equations to describe them. And now we have an equation for a plane in space. So now let's get tricky. Let's get tricky next. So when we're talking about planes in space, a couple of things can happen when you have more than one plane in space. So two distinct planes in space are either what? One, they can be parallel, or two, they can intersect. What happens when two planes in space intersect? Well, they create a line. Okay. Just like in 2D space, when you have two lines that intersect, they intersect at a point. Well, in 3D space, when you have two planes intersect, they intersect in a line. Okay, and so that's interesting in itself. What we need to be able to do with this, to do calculus, is we need to be able to determine if two planes intersect, the angle at which they intersect. Okay, so let me try to draw a picture here. Let's see how I do. Okay. All right, so I've got okay, so you can kind of see what's going on here, right? Okay, so I've got two planes. I've got this guy here that runs kind of up the page, and then I've got this other plane that runs horizontal on the page. Okay, and there's some angle between these two, right? Obviously, you can see they intersect in this line here. Okay, and there's some angle here between them, right? Some angle theta. Right, so that's the angle that would be interested in knowing. Now, obviously, if you know this angle, then you must know the angle over here. It's 180 minus whatever that angle is. So which angle you get is irrelevant. If you get one, you get all you need to get any of them. Okay, and so the angle, so we are interested in knowing theta. Okay, and the theta is going to be some angle between 0 and pi over 2, right? Right, this is obviously an obtuse angle here, but this is acute, right? So there's always going to be one of the two that's acute, right? Maybe both if they're both 90 degrees. Okay. Okay, so one of the nice things about this, one of the clever things about this is that the angle between the planes can be identified by identifying the angle between their normal vectors. Okay, so if I've got some vector here, which I'll call n1, which is normal to this plane, and some other vector here, which I'll call n2, and this other one is kind of, I'm going to think of it as kind of cutting through this plane and being normal to this plane on the bottom. Okay, then the angle between these two vectors is the same as the angle between the planes. That's hopefully obvious, I guess. I mean, if you take a step back and think about it, right? The vectors are normal to the planes. If the planes are tilted with respect to one another, then obviously that whatever degree that tilt happens to be is going to translate into the normal vectors as well. Okay. All right. So if n1 and n2 are normal to the two intersecting planes, this angle theta between the normal vectors is equal to the angle between the two planes. Okay, so theta, why do I keep writing Q? Theta is the same between n1 and n2 and between the two planes. Okay, now we talked about how to find the angle between two vectors previously, and what we said was that we could use this. Cosine of theta is equal to n1 dot n2, take the absolute value of that, and divide by the norms of the two vectors. Right, so you can dot the vectors, you get some constant on top, and then you get so you get a scalar on top, and then you get two scalars on the bottom, multiply them together, do the division, and there you go. Okay, and so this can obviously be used. You get some scalar over here, you take the inverse cosine to find theta. Okay, and a couple of things. So if the planes are perpendicular, what does that mean? If the planes are perpendicular, what's the dot product? Okay, so if the planes are one perpendicular, well, what does that mean? That means n1 dot n2 is 0. Okay, and what happens if the planes are parallel? These are kind of the extreme cases with these, right? At these intersecting planes. If the planes are parallel, then the normal vector 1 is going to be equal to c times normal vector 2, for C and R, for some C and R. Right? But it's basically they're going to be, one's a scalar multiple of the other. Okay. If they're parallel. Hopefully that makes sense, right? I mean, if you got one of the planes like this, and the other plane is like right below it, then you got n1 here, and you got n2 here. Obviously, they're in this identical direction. They just may vary in length. Okay, so there's some scalar multiple of each other. Okay, so that should be clear. All right. Let's do an example. Let's see how all this plays out. So this is the key thing to know. This is a nice picture to keep in mind. Okay, this will be the key computational piece that we'll need. Okay. So let's do an example. So in this example, we want to find the angle between the two planes given by x minus 2y plus z equals 0 and 2x plus 3y minus 2z equals 0. Okay, so we want to find the angle between these two planes and find parametric equations. Find parametric equations of their line of intersection. Okay, so that's the idea. Right, so what we want to do is we've got these two planes, we're given the equations of both of these two planes. We want to find the theta between them, the angle between them, and we also want to find the equation of this line where they intersect. Okay. All right, let's do that. Okay, so from the given equations, so we're given the equations of the planes, right? Those are the two equations that are given. Now remember how we constructed those, right? The coefficients for x, y, and z are you can think of them as the components of the normal vectors. Okay, so n1 would be 1, -2, and 1. Right, just reading them off here: 1, -2, 1. And the second normal vector would be 2, 3, -2. Just read right off of the equations. When they're in this form, they're very easy to work with. Okay, so we know the two normal vectors. We can easily find the angle between the planes using the identity we just described. So then the cosine of theta would be equal to n1 dot n2, absolute value, and then the norm of those two. Okay. So let's calculate these things separately. So n1 dot n2. Okay, what's n1 dot n2? Well, it's let's see, 1, -2, 1 dot 2, 3, -2. Okay, and we get 2 minus 6 minus 2, so -6. Okay, and so that means you've got -6 in the top here. And then what are the norms of the two vectors? N1 norm is 1 squared plus -2 squared plus 1 squared again. So looks like you get square root of 6. N2 norm is 2 squared plus 3 squared plus -2 squared. And so that's what, 9 plus 4 plus 4, so that would be the square root of 17. And so those can go in here as well. And then away you go. So 17 times 6, so 6 times 7 is 42, so that's 102. And so this would be 6 over the square root of 102. Okay, and so just kind of jumping down here, so theta is the inverse cosine of this. All right, so you can go out and find that number. Right, it's about 55 degrees or so. Something like that. Okay, so that's kind of the easy part of this example, right? So given the two planes, the equation of the two planes, go and find the angle between them. All right, now what about the equation of the line that of intersection for these two planes? Okay, what about that? So what about the equation of the intersection line? Well, you know from just regular two-dimensional algebra, right, that if you want to know the point where two lines intersect, you have to solve the two, you have to set the equations equal to each other and solve them simultaneously, basically, right? And so it's going to be similar here, right? You've got the equations of the planes. You're going to have to somehow solve them simultaneously. Okay, so we need to solve x minus 2y plus z equals 0 and 2x plus 3y minus 2z equals 0 simultaneously. Right, to find the intersection. Okay, and so one way you can do this, again, if you have had some linear algebra, you're probably thinking to yourself like, well, I could easily just plug these into a matrix and and you'd be right. But we haven't really had that. So what we're going to do is we're going to use kind of like the algebraic techniques that we've seen thus far, things that we're used to, right? So if I take one equation like this, and I subtract the other one or add the other one to it, I get a third equation, right? So 2x plus 3y minus 2z equals 0. Now, I'm not going to gain anything in doing that, but I would gain something in doing that if I first multiplied this entire thing by negative 2. Right? Because then I can eliminate this x variable, can't I? Right? So if I do that, then I'll have negative 2x plus 4y minus 2z equals 0, and I'm going to add to that 2x plus 3y minus 2z equals 0. Right? I'm going to add those together. So the x's will cancel each other out, and I'm going to just have 7y minus 4z equals 0. Okay, and so from this, right, so that's going to imply that 7y equals 4z, and y equals 4z over 7, right? So that's the first piece. Okay, so that's the first piece. Now, what I can do then is I can take this. So let me grab another sheet here. Okay, so we know that y equals 4z over 7. Okay, so I can substitute this quantity back into one of the other expressions, right? And so I'm going to substitute this. I'm going to substitute that into x minus 2y plus z equals 0, right? It's one of the original equations. And so what do I have? I get x minus 2 times 4z over 7 plus z equals 0. Okay, and so that means x minus 8z over 7 plus z equals 0. All right, so I can simplify this down until I get, this will be x minus, now 8z over 7 plus 7z over 7 is 1z over 7, right? So x minus z over 7 equals 0, and so that's going to imply that x is equal to z over 7. Okay, all right, so I've got this one and I've got this one now. Okay, and so I've also got basically I can come in here at this point and I can say let's introduce a variable t. And we'll let t equal z over 7. Okay, and what does that give me? Well, now I know that x is equal to t, y is equal to 4 times t, okay, and z is equal to, well, I can derive it from this guy here. Z is equal to 7t. So these would be my parametric equations for the line that is formed when the two planes intersect. Okay. All right. Okay, perfect. Well, this one, this one you can get it different ways, but I mean, I guess the easiest way is to just derive it right off of that, right? Just to make sure that was clear. Okay. So just say, at this point, z is equal to 7 times t. Just kind of move that over there, right? Okay. So I want to make sure. Sometimes I go a little fast and... Okay. All right. Very good. And so given this, this is the equation. These are the parametric equations for the parametric equations for the line of intersection. What you could say is that 1, 4, and 7 are the direction numbers for the line of intersection. Right? So you can see how you could talk more and more about this. So 1, 4, and 7 are the direction numbers for the line of intersection. Okay. All right, very good. So that was a great example. That is, so now we know how to write equations for lines in space. We know how to write equations for planes in space. And now we know how to identify when planes intersect, what the angles between them happen to be, and also how we can find those lines of intersection as well. Okay. One of the things about dealing with planes in space that can be very tricky is just kind of how to sketch them or think about them. Okay, so sketching planes in space. Can be tricky. Okay, so it can be tricky. And so one of the things that we kind of introduce here, which will definitely come up as we're doing more and more problems, is the idea of how to sketch these things efficiently, how to develop some intuition about them. And I mean, the main source of efficiency in terms of sketching planes is the idea of the trace of a plane. Okay, so if a plane in space, obviously, if a plane in space intersects one of the coordinate planes, right? If it intersects one of the coordinate planes, we call the line of intersection the trace. We call the line of the intersection the trace. Okay. Okay. And so this is useful when you're sketching planes. Basically, the way we want to do it is, so to sketch a plane, in space, you want, basically two things. First, you want to know the points of intersection with the coordinate axes. The points of intersection with the coordinate axes. Okay. Right. Normally, like most planes, will just intersect each coordinate axis in one point. Right. I mean, you could have other cases, right, where a plane in space is one of the coordinate axes, in which case it'll intersect at all of the points. But those are kind of like the edge cases, right? The typical case is where a plane is just kind of thrown in there somehow, and it crosses the x-axis, and it crosses the y-axis, and it crosses the z-axis. And where it crosses, those are the points of intersection with the coordinate axes. So that's the first thing that's useful. The second thing is to know its trace in the coordinate planes. Okay. Now we'll talk about this in a sec. So what does this mean? Okay, let's do an example here. Okay. This will be kind of a working example. All right, let's consider the plane given by 3x plus 2y plus 4z equals 12. Okay. if we want to find the xy trace, if we want to find the xy trace, the way we do it is you basically just have to set z equal to 0, right? And so that's going to tell you, like, if it, basically you're taking the plane and you're kind of dropping it down on the z-axis, and what you find is what's left over is the line that intersects the xy plane. Okay, so set z equal to 0. Okay, and so what do you get? You get 3x plus 2y equals 12. Okay, so then from the xy trace, we can identify the y-intercept and the x-intercept very quickly, right? So to find the y-intercept, we would just want to solve for y. So you'd have 2y equals negative 3x plus 12, divide everything by 2, y equals negative 3 halves x plus 6. Hold on, plus 6, yep. So this is your y-intercept. Okay, so it would intercept the y-axis at 0, 6, 0. Okay, what about the x-intercept? It's going to be the same thing, except you want to solve for x. So here we would say 3x equals negative 2y plus 12, and so x equals negative 2/3 y plus 4, and so your x-intercept is 4, 0, 0. Okay, now let's draw this on here and see what this looks like. Okay, so I'm going to draw out my three-dimensional coordinate system, my x, my y, and my z. Okay, and I've said that the plane I'm interested in intersects the x-axis at 4, 0, 0. Right, so 1, 2, 3, 4, so it's right there. 4, 0, 0. And the plane I'm interested in intersects the y-axis at 0, 6, 0. So 1, 2, 3, 4, 5, 6, so up here. And so we can draw the trace. Right, so that's the line that intersects the xy plane, right? You can see it's on the xy plane, and so our surface is going to come down and intersect the xy plane along this line. Now, what about up here with the z? How do we get to that? Okay, well, you could get to it by the xz trace or the yz trace. So let's use the yz trace. Okay, so the yz trace can be found by setting x equal to 0. Okay, and so I get, what do I get? I get 2y plus 4z equals 12. Okay, I just need to solve for z, right? So 4z equals negative 2y plus 12. Z equals negative 2 over 4y plus 12 over 4, which is 3. So the intersection here would be 0, 0, 3, right? Okay, so 1, 2, 3. It's going to cross right there. Okay, and you could confirm this by using the xz trace. You'd get the same answer, right? But now you can see how the plane intersects the xz axis here, and it intersects the yz axis there. Okay, and so you can now visualize where this surface lies in space. Okay, and so this would be a good sketch of a plane in space. Like, you have to be careful. These are planes in space. They're not easy to sketch, so you got to try to keep it simple. And so I think this is the best way to do it, to just kind of identify the three coordinate intercepts, coordinate axis the coordinate axis intercepts, and just draw the traces that intersect those three. Okay. Okay. So This is kind of the normal case. Occasionally, you'll come across equations for planes that'll have missing variables. What does that mean? Occasionally, you will have equations with missing variables. Okay, a missing variable. What that is going to indicate is that the space is parallel to the axis. This means the plane is parallel to the axis. Okay, right? So for example, let's draw a picture here. Okay, so if I had it intersect here and here, okay, and then let's just say the plane extends this direction, right? And it never crosses. This is the x, y, and z axis. It never crosses the y-axis, right? This plane here could be represented as 2x plus z equals 1, right? So here the y variable is missing. Right? What does that mean? Well, it means that the plane is parallel to the y-axis. It never crosses the y-axis. It's totally independent of the y-axis. Okay. Now, so that's the case where you have a plane that's parallel to one of the axes. It can also be the case that your plane is parallel to more than one axis. Right? Let's do an example like that. Let's see what that would look like. So if I have a plane that looks like this, maybe ax plus d equals 0. Right? So I just have the x variable, no y or z. This implies the plane is parallel to the yz plane. Right? It's not going to intersect the y-axis, and it's not going to intersect the z-axis, right? So if you were to try to draw this, x, y, z, so it's going to intersect the x-axis, right? But then it's just going to go like this. It's just going to it's going to exist in this, like this, right? It's going to run parallel to the y-axis, and it's also parallel to the z-axis. Okay, so it never crosses them. It just sits out here on the x-axis, and that's where it is, and it never crosses the y-axis, never crosses the z-axis. Okay, so this point here could be, it'll intersect the x-axis only, and specifically at what, ax plus d equals 0, which it would imply that x is equal to negative d over a. So it'll intersect at negative d over a, comma 0, comma 0. Okay. All right. Very good. Okay, so this will have to be a two-part video, so I'm going to pause here and then we'll resume in part B in a moment.